In this video, we'll be reviewing limits at infinity, i.e. asymptotes, horizontal asymptotes. We'll also look at vertical asymptotes, and later on we'll look at oblique asymptotes. So most of this should be a review. So it's going to be a short lesson. Alright, this is the official calculus definition of a vertical asymptote. We know from pre-calc that a vertical asymptote is just a line that a function approaches but does not cross, a vertical line that you approach but do not cross. So here in calculus language it says if f of x, so if the function approaches infinity or negative infinity as x approaches c, so that looks like if this is c here, your function going to infinity, so f of x approaching infinity, or negative infinity as x approaches c from the left or right. So if that's happening, then you have a vertical asymptote. An important theorem, vertical asymptotes exist when, if this is your function, it exists when g of x is, sorry, not g of x, g of c here equals 0. So you have a vertical asymptote at x equals c, a vertical asymptote at x equals c, you can see that part, when g of c is 0. So basically it's saying we want our denominator to equal 0 in order to have a vertical asymptote. The key thing here is f of c, the numerator, cannot be equal to 0 because we can't have 0 over 0. If we do, if we have that situation, we have a hole. And we'll take a look at an example like that. Okay, so quick review, finding vertical asymptotes. Here's our function. We have vertical asymptotes when the denominator equals 0. So 0 equals 2 times x plus 1. Divide both sides by 2. 0 equals x plus 1. So x equals negative 1. That's our vertical asymptote. So remember, that would be our asymptote as let me draw a little sketch here. So our function is going to look something like this. At x equals negative 1, we have a vertical asymptote. So the function gets infinitely close to it, but doesn't cross. So f of x is going to infinity as we get close to c. F of x is going to negative infinity as we get close to this c value here. Alright, in b, in order to figure out when the denominator is 0, we're going to have to factor. We should always factor when we're thinking about asymptotes. Alright, so in the denominator, this is a difference of squares. Pattern, x plus 1, x minus 1. In the numerator, we have the sum of squares. That's not a pattern. It's not factorable. So this has to remain x squared plus 1. So there are no factors that cancel here. Next up, we want to set our denominator equal to 0. So 0 equals x plus 1 and x minus 1. Set each factor equal to 0. And 0 equals x minus 1. So you have vertical asymptotes at, over here we'd have negative 1, and up here, positive 1. So we have two vertical asymptotes for b. For c, we have to think about trig functions. Alright, we know tangent of x is equal to y over x, or opposite over adjacent, which is sine of x over cosine of x. That means cotangent of x is just the reciprocal. It's cosine of x over sine of x. Alright, so let's clear that out so that we can actually use that fact. So, we're going to rewrite cotangent of x. So f of x equals cosine of x over sine of x. We want to know where there are vertical asymptotes. That means we need to know when the denominator equals 0. So set 0 equal to sine of x. We want to ask ourselves, when is sine equal to 0? Well, unit circle. Sine is the y value. Oops. Here we have a x value of 1 and a y value of 0. Over here we have an x value of negative 1 and a y value of 0. So this is 0 degrees or 0 radians and 180 degrees or pi radians. That means that x here is 0 radians, pi radians. If we rotate it around to 2 pi, we'd have sine of x equals 0 again. So this is a pattern. It can be expressed, I'm going to erase this just so we have a little more room. It can be expressed as pi k, where k is an integer. Remember that kind of notation? The important part is pi k. The integer, k being an integer, is sort of implied. Alright, I'm going to erase that so we have a little more room for D. Okay, so in D, we are going to have to factor. Remember, we want to factor the numerator and the denominator. So I'm going to mentally do a diamond for the numerator. This is what I get. In the bottom, I have a difference of squares. So x plus 4, x minus 4. Alright, so this denominator is 0 when x is negative 4. But that would also make the numerator 0. We don't want 0 over 0, so we cancel these out. It turns out a canceled factor creates a whole, and that's going to be at negative 4. But we still have this x minus 4. We want to know when is that equal to 0. So 0 equals x minus 4, x equals 4. That's your vertical asymptote for D. Next up, we have horizontal asymptotes. Vertical ones were vertical lines that we approach but could not cross. Horizontal ones tell us where we are going as x approaches infinity or as x approaches negative infinity. So let's clear up a little space here. Okay, in this picture we can tell that as we go to negative infinity, as x goes to negative infinity, our function is headed towards 3. And as x goes to positive infinity, our function goes towards 3. So our horizontal asymptote here would be y equals 3. We can think of that in terms of limits, right? Asymptotes, horizontal asymptotes, are really just about limits at infinity. So the limit as x goes to negative infinity of f of x is 3, and the limit as x goes to positive infinity of f of x is 3. We can also see it in a table here. So starting at 0, we can see the values getting bigger and bigger and bigger. It's implied that they're headed towards 3 because it's getting closer and closer and closer to 3. Same thing here. Our values are getting bigger and bigger and closer to 3. So we can find asymptotes, horizontal asymptotes, graphically with a table or with limit notation, so with algebra. Alright, next page. So let's put what we know about horizontal asymptotes to work. In pre-calc, we talked about top-heavy, bottom-heavy, and balanced equations. We're going to do the same thing here. So looking at A, this is bottom-heavy. The degree is bigger on the bottom than it is on the top. That means that our horizontal asymptote is 0. Now remember, this is the same thing as saying the limit of the function f of x as we go to plus or minus infinity for x is equal to 0. It means the same thing. Alright, next up, let's look at B. And the degree here is balanced. Balanced. So we divide, and we get y equals 2, because 4 over 2 is 2, and the x squareds cancel, because it's balanced. So again, this means as we go to positive infinity, as x goes to positive infinity, as x goes to negative infinity, our function is approaching 2. Alright, looking at C, this is top-heavy. That means there is no horizontal asymptote. Instead, it's going to have an oblique or slant asymptote. We will need to learn long division of polynomials in order to do that, though. So for now, we're just going to say there's no horizontal asymptote and leave it at that. Okay, the final two important examples. D has a square root in the denominator. And inside that square root, we have an x squared. Now this is interesting because it means that if x is negative, the 2x squared becomes positive in the denominator. But a negative x would make the numerator negative. So we'd have a negative over a positive. But if your x value was positive, your 8x would be positive and 2x squared would be positive. So we actually have to consider two different scenarios here when we think about horizontal asymptotes. There's going to be one asymptote for x values that are negative, so as we head to negative infinity for x, and then a scenario where x is positive as x goes to positive infinity. Okay, so let's start with a positive example. We've got the limit as x goes to infinity, because we're thinking about horizontal asymptotes, of 8x minus 1, and we're actually going to divide both the numerator and the denominator by x. So I have the square root of 2x squared plus 1 divided by x. Now, unfortunately, this does not simplify nicely. So instead of leaving it like that, we are going to actually do something equivalent to x, which is the square root of x squared. Once I have that, I can actually combine these radicals together into one big radical. So I have 2x squared plus 1 over x squared. Alright, so let's simplify this. And this is still a limit. Oops, I should have put in my limit notation here. X is still going to infinity. So let's keep that. The limit as x goes to infinity of 8x over x. And 8x over x would just simplify to 8, and then minus 1 over x, all divided by, and we have the square root, 2x squared over x squared, plus 1 over x squared, which gives us the limit as x goes to infinity of, well, we said 8x divided by x is just 8, minus 1 over x divided by the square root of 2 plus 1 over x squared. Now, when x is going to infinity, 1 over infinity here just makes this 0. It cancels. 1 over infinity squared here, that's just 0. So, we are left with not very much room, apparently. Okay, I'm going to go right down here. So, we are left with the limit as x goes to infinity of 8 divided by the square root of 2. So that's our horizontal asymptote, y equals 8 over root 2 for the right-hand side. Now let's think about what this would look like for the left-hand side as x becomes negative. So instead of erasing and rewriting everything, I'm just going to think about what needs to change for the negative scenario. So I'm going to change this to x approaching negative infinity. We know that the 8x would become negative. So let me actually do it this way. When I divide by x, I'm dividing by a negative value. Here, it's still negative x squared, which doesn't change the fact that that becomes a positive x squared. And let's put in our negative sign up here. Okay, so then we still have the limit, but we're going to negative infinity. And this is a negative x, so this becomes a negative 8 down here. Negative 1 divided by negative x becomes a plus, so plus here. And in the denominator, nothing changes. Okay, so we still have the limit as x goes to negative infinity is negative 8 plus 1 over x, which now 1 over infinity goes to 0. And then same thing here, we still have the square root of 2 plus 0. The difference here is this becomes a negative 8 over root 2. So the horizontal asymptote is negative 8 over root 2 as x goes to negative infinity. Okay, so in your work, you should have two separate scenarios, the positive and the negative, and not just change negative signs like I did. I just ran out of room. Okay, final example, we have a trig example. Let's clear this board. Okay, so here, f of x equals sine of x over x, looking for a horizontal asymptote, you just need to know your identities. This one, the limit, as x goes to positive and negative infinity, for sine of x over x, the limit is 0. There's no other work to show for that. You just need to know your identity. So that means your horizontal asymptote is y equals 0. And here we had y equals plus or minus 8 over root 2. All right, that's it. Oblique or slant asymptotes we're going to save for another time. Thanks for listening. Bye.